Well, this is another of my most favourite pictures, I think, in astronomy. It's a picture of a galaxy, a very average galaxy, about 50 million light years away. There are probably 100 billion suns in that galaxy, about, what, a billion in the galactic core. So that's shining with the light of a billion suns. But this star here is very interesting because that star is in that galaxy. It's 50 million light years away, but it's shining as brightly as a billion suns in the centre of the galaxy. How can that be? What could possibly have caused that to happen? Well, this is an exploding star. It's called a Type 1a supernova explosion. And it's a very special kind of supernova because what we think happened is that a star got to the end of its life, so a star like the Sun, it had used up all its nuclear fuel, it burnt hydrogen into helium and then started burning helium into carbon and oxygen, the elements of life. So they entered the universe for the first time in stars like this. I'm going to say something more about that in a moment. But then the star eventually ran out of fuel and could not do anything else. It couldn't create more energy in its core, so it just sat there and became something called a white dwarf star, which is a very small star that, like the core of our sun, exposed with all the outer layers blown off into space. But this star had a companion around it, a big gaseous star, which it began to suck matter off until it got heavier and heavier again, until it could no longer stand up against its own weight. It couldn't remain stable, and so it exploded. Now, those kind of supernova explosions are very important because they always shine with the same brightness, right? So we know, because we understand the physics of how stars work, the science of stars, how bright those explosions must be. And that means that we can measure how bright they are from the Earth. So we can stand here and say, well, that looks, well, quite dim. But we know how bright it was. So we can work out very easily how far away it was. And actually, these explosions occur throughout the universe. So this is a picture, just again from the Hubble Space Telescope, of lots of different galaxies here. And in each one, over a period of a few weeks, a new star has appeared in the galaxy. So there's a star that wasn't in this picture. There's a star that wasn't in this picture. There's one that wasn't in that picture, and so on. These are all those kind of supernova explosions, and they all have a particular brightness. And so we can use them to tell us how far away these galaxies are. Literally, the dimmer that explosion looks, the further away the galaxy is. So that's the second piece of evidence. We can measure how far away the galaxies are. And from the redshift, we can measure how fast they're flying away. Because the faster they're flying away, well, actually I should say, the more space is stretched, then the redder that light becomes. So we can put that all together into a story. Right? What we find is that the further you look out into the universe, the faster things seem to be flying away. So in other words, the more space is stretched. And it's very interesting because that is exactly as you would see if you got, let's say you got a loaf of bread with loads of raisins in it and put it in the oven. And then the bread cooks and expands and all the raisins fly away from each other. Now, if you stand on any one raisin and look at the others, then you would see them all flying away from you because the bread is expanding. But also you would see that the further away from you those raisins are, the faster they go away from you. You might have to think about that for a bit, but just think about that loaf expanding. The closer raisins start moving a little bit, but if you're further away and everything stretches, then the further away ones will move faster and faster and faster. That's what we see in the universe. So those two things tell us that everything is flying away from everything else. The further away you look, the faster that's flying away. That tells you that the universe must have been smaller in the past, just in the way that if you had a loaf of bread and you cooked it, then it starts off small and then it expands as you cook it. So that's the interpretation of those two pieces of evidence, looking at the supernova, looking at the fact that light is stretched. That means that the universe must have been smaller in the past. The universe must have been smaller in the past. And we can run that video back because we have such a precise map of how far everything is away, how far it's flying away. We can run back time and we can look and see, well, quite literally when everything was on top of each other. Was everything on top of each other? Does everything seem to rewind back properly? Well, you find that it does. And you find, if you stick all that into a computer, put all those beautiful measurements in and run it back in time, that everything looks like it was on top of each other about 13.7 billion years ago. So redshift, that fact that light is stretched, and the fact that the further away you look, the faster everything seems to be moving away, so the more stretched everything seems to be, tells you or suggests that the universe might have had a beginning. So that's one piece of evidence for the Big Bang. But that's a pretty bold thing to do, isn't it? It's a pretty bold thing. So I think the universe had a beginning because light looks a bit stretched, and if you look farther away, things are stretched a bit more. Well, there's more evidence than that. As you go back in time, so what's the most distant thing you can see, you might ask? Well, go back from 1 billion years, 2 billion years, 3 billion years, keep going and try to see the most distant light you can find, the most stretched light. Well, we've done that and we can see it, and it's this light. This is a picture of the sky called the cosmic microwave background picture. It's a picture of light that we think was emitted from the universe 370,000 years after the Big Bang. Now, how do we know that? Well, before that time, we think the universe was so dense, the galaxies was, well, there weren't galaxies, but all that matter was stuffed into a very small space. It was all kind of on top of each other. It was so dense that light couldn't get through it, right? So the universe was completely opaque. It was like the fact that light can't get through that wall there because it's too dense. You can't shine light through it. In the same way, the universe was denser than that wall, so light couldn't travel. But 370,000 years after the Big Bang, then the universe became cold enough and less dense enough, essentially, diffuse enough that light could travel through it. And that light has been traveling through the universe ever since. We can detect it and we can take a picture of it. And one remarkable thing is that we can measure exactly the temperature of that thing. Because remember, earlier on in the lecture I said that the colour of the light tells you the temperature of the thing that emitted it. Well, we can measure it, and this is an actual plot of the data of the wavelength of this light. And it's this beautiful shape. It's called a Blackbody Spectrum. And it's actually the temperature of something that emitted light, well, it's now 2.7 degrees above absolute zero. And it's absolutely perfect. Now, the universe has been expanding for a long time, 13.5 billion years since that light emitted. And the universe has been expanding and cooling down. But there's still this echo of the Big Bang left. You can see that the universe once used to be very hot and has then expanded and cooled. And you can see that it's perfectly the shape of something that's just glowing, a faint cinder, essentially, that began very hot and has cooled down and cooled down and cooled down. So the interpretation of this strange light is it's at the afterglow of the Big Bang. You're seeing that explosion 370,000 years after it happened, when the universe was incredibly hot and incredibly dense. It's cooled down ever since, but it hasn't cooled down completely. It's still sat there. So that's the second piece of evidence for the Big Bang. I just want to give you one more piece of evidence because it's perhaps the most remarkable piece of evidence of all. This is our picture, my picture of the Big Bang. The universe beginning 13.7 billion years ago and expanding and cooling. And today, 13.7 billion years later, we have stars and planets and people like us and civilizations. As you go back in time, the universe gets hotter and hotter, so the Big Bang theory goes. At 370,000 years, the universe was dense enough so that light couldn't travel through it anymore. So this is the place where that light that we've captured from the Big Bang came from, that incredibly hot surface, and the light has been emitted and captured. As you go back in time, though, to about 3 minutes after the Big Bang, we still understand the physics, remarkably, that happened then. And we understand how the lightest elements were produced. So we think that when the universe began and it cooled down sufficiently, the lightest things in the universe, hydrogen, helium, lithium, those elements, just the first 3 elements were formed, but no other ones. And we can calculate precisely the different amounts of those. And we get a very precise calculation based on our assumption the universe began at the Big Bang in a very hot, dense state. The universe should be about 75% hydrogen, 25% helium. Very precise numbers. And we can measure that by looking at the elements in the stars from the light in the distant galaxies, and we get the right answer. So we have another piece of evidence, the fact that from what we understand, the elements in the universe, the very light ones, should have been created in the first 3 minutes of the universe's life, and we can make the measurement, we have a prediction, and we get the answer.